is AI Talks, your regular monthly shot of ML vaccine, 100% efficient and useful information on the machine learning tools and know-hows. My name is Daniel, and I'm your tonight's host. Today, we will be talking about one of the ever-futuristic topics in all the IT universe, about sharing and shaping of our perception of physical reality with the help of machine. Our tonight's speaker, Vitalii Vorobyov, will demonstrate to which extent this enhanced reality has already impacted our life and our work as data scientists. We will discuss vectors of development of this technology and cover the successful cases of XR adaptation in the industry consumers market. Moreover, we will investigate the classic computer vision algorithms for AR and dive into the use cases of AR-related deep learning. Finally, you will get to know the XR solutions which we are developing at SoftServe. Greetings, Vitalii. How are you doing? Please go ahead and share your screen. I will be stopping sharing. And
hello,
the stage is yours. Thank you.
Okay, hello guys. Can you see my screen now?
Yes, nice and clear.
Okay, so hello. Today in our talk, we will talk about what XR is and which technologies it contains. I will show where it can be used and will cover some solutions which were made here at SoftServe. After that, I'll give a general idea about how ML can be used in this sphere with some examples. And the main part of the speech is a deep review of popular classic computer vision algorithms which are widely used in AR and MR. At the end of the presentation, you will be able to try AR yourself using your phones. I want to emphasize that during our presentation, we will have some interaction, so be ready to have your browser tab opened at menti.com link in the next couple of minutes. Or you can use your smartphone and scan the QR code which I'll provide on the next slide. So let's start. And here is our first quiz. Please go ahead and answer a little bit tricky question. What do you think XR means? You can scan QR code on the left panel to access the quiz via your phone, or you can navigate to menti.com link and use the code which is below on the slide. We will now leave a few seconds to wait while people are joining the quiz, and after that I'll start it and you will have a few seconds to answer it. So, okay, we already have some people. Let's wait for some more.
Could you go back just for 1 second? I need to get the QR code for me.
Oh, okay.
Thanks.
Okay, so we already have a lot of users, so I think we can start our quiz now. Okay, so we actually have some interesting results. A lot of people said that XR can be a virtual reality. Some of them said that it is an augmented reality, and some of them picked that it is a mixed reality. But actually, the right answer was that it is a placeholder name for all of those three technologies, for augmented reality, virtual reality, and mixed reality. So let's proceed back to our presentation. So actually, extended reality, or shortened XR, refers to all real and virtual environments generated by computer graphics and variables. The X letter in XR is simply a variable that can stand for any letter from the list of technologies that XR can offer. Extended reality is the umbrella term that covers all the various forms of computer-altered reality, including augmented reality, shortened for AR, mixed reality, MR, and virtual reality, VR. So we already know what XR means and that we have to deal here with 3 different technologies. But what exactly the difference between them? To be short, the main points here are the 2. The first is how actually user interacts with this technology, and the second one is how immersive this technology is, or in the other words, how much virtuality it brings to us. From this chart, we can see that the closest to reality and most familiar to us is augmented reality. After it goes mixed reality, and finally we have virtual reality. And now let's take a closer look at the 3 of them separately. Augmented reality does exactly what it sounds like. It is a reality enhanced with digital components. The most commonly used AR applications these days rely on smartphones to showcase the digitally augmented world. Users can activate a smartphone's camera, see the world around them on the screen, and rely on AR application to enhance that view in any number of ways, like superimposing images, adding real-time directions, inserting labels, changing colors, and etc. Currently, AR technology is mostly mobile-based, so there are only 2 popular platforms: Android devices that use AR Core SDK for the development of applications, and iOS devices which use ARKit framework. Also, a small part of the market is occupied by other devices which are intended for use in specific conditions, such as Ashen T1 device, which is produced by a RealWear company, Vuzix Blade, or Google Glasses. Usually, those devices don't support previously mentioned frameworks. Therefore, all augmented reality algorithms for them must be written from scratch. The next, in our case, is mixed reality. It is when real and virtual worlds merge together to produce new environments and visualizations, where physical and digital objects coexist and interact in real time. It is based on advancements in computer vision, machine learning, graphics, display technology, and input systems. At first, it may seem that augmented reality and mixed reality are the same, but the key difference is that augmented reality cannot actually interact with virtual objects. They only provide an overlay function. But in mixed reality, you can freely interact with them, which overall gives more immersion. Today, there are only 2 popular platforms for mixed reality. The first one is Magic Leap glasses, which are produced by Magic Leap company, and they run on Lumen operating system, which is based on Linux. And the other one is the HoloLens glasses, which are produced by Microsoft, and they use Windows Mixed Reality operating system, which is the part of Windows 10. The next is virtual reality, and it refers to a fully computer-generated simulation in which a person can interact within an artificial 3-dimensional environment using wearable devices such as special VR headsets fitted with sensors. Unlike augmented reality and mixed reality, virtual reality doesn't have any interaction with real world at all, unless you hit your table with a controller while playing Beat Saber. This technology is the most common in games because it allows you to fully immerse yourself into the gameplay. Virtual reality is the only area that boasts a wide selection of devices. Here I have only listed the most popular, such as Oculus Quest, PlayStation VR, Valve Index, and HTC Vive. Now let's move to the next part of the presentation. Where is it used? At first glance, it may seem that besides games, these technologies are difficult to apply elsewhere, but this is far from being the case. They are being already successfully used in industries such as healthcare, marketing, retail and e-commerce, education, and more and more and more. And now I want you to be a little bit attentive because we now move to the next quiz of our presentation. So please prepare your phones and browser tabs again. Here is the next quiz. And the question is, which domain, not necessarily from those which were on the previous slide, do you think needs mixed reality technology so much that Microsoft has signed a contract to deliver 120,000 units of HoloLens headsets? This question is even more tricky because it is an open question, and please feel free to write your own answer. Okay, so we need to wait people to go to this quiz a little bit.
I think you should allow the question to start.
Okay, 1 minute.
Yep. There we go.
Okay, so we have a lot of answers. So actually the current answer was military, and there are several people who answered it correctly. Also, we have some interesting cases like healthcare, retail, food and beverage, medicine. Oh, also there was US Army and soldiers. So a lot of you were right. So let's continue our presentation. Yeah, it was really just less than a month ago, actually on March 31st, the United States Armed Forces said that Microsoft had won a contract to build custom HoloLens headsets for their needs. The contract was signed for over 120,000 headsets and could have been worth up to nearly $22 billion over 10 years. The EVAS, which is the name of this headset, which stands for Integrated Visual Augmentation System, is a special headset based on HoloLens and powered by Microsoft Azure Cloud Services, which delivers a platform that will keep soldiers safer and make them more effective. The headset enables soldiers to study and to fight in one system. This deal shows us that XR technologies have already developed so much that they can and are already used in such complex areas as the military, and where reliability and safety comes first. The next use case is the mixed reality and healthcare. And here is our internal soft-serve development, which is used in healthcare, and it is called XR Molecular and was developed by our R&D team. Soft-serve XR Molecular is a combination of artificial intelligence and mixed reality that provides users with easier and quicker way to create, visualize, and explore the nuances of molecular structure in one solution. This solution can help scientists to show molecules with design scalability, manipulate molecules to rotate them, scale, and cut, measure distances, angles, torsions, and show some interesting metrics to them. The next use case is also our internal product named Reskill, which was developed by XR Group team, and it is used widely in manufacturing sphere. It is an AR platform which enables frontline workforce to perform at their best and improve continuously with intelligent training, support, and guidance. Workers in production still use a lot of paper instructions to solve some problems with equipment, and when they fail to do so, production could be stopped from several hours to several days until an expert arrives to the location and helps to repair everything. With this solution, you don't have to wait so much time. It not only provides you with detailed instructions using augmented reality with the help of HMD1 headset or HoloLens headset, but can also help you to connect with the expert, and he will be able to help you in real time from his office. Now let's talk about the usage of machine learning in extended reality. We already know that machine learning can be used in XR based on the examples of our developments such as XR Molecular, where machine learning is used for data generation, DocAI, where machine learning is used for document management, a visual inspection tool which has a pretty good anomaly detection pipeline. But the question arises whether is this all for what you can use machine learning? In fact, the use of machine learning in extended reality is not as popular as it might seem. The main part of the immersive job is done by classic computer vision algorithms, about which we will talk a little bit later. Often, machine learning is used as an auxiliary tool for some data processing. However, there are still some cases where machine learning performs better than classical computer vision. And one of these cases is real-time hand tracking. Precise hand tracking will unlock a range of new experiences. People could be able to pause a movie in virtual reality with body gesture, for example, and express themselves more naturally in social games. In enterprise applications, an instructor could lead a virtual reality-based training class without having to maintain a fleet of controllers, which are known to have issues with pairing and charging. Deep neural networks are used to predict the location of a person's hands, as well as landmarks, such as joints of the hands. These landmarks are then used to reconstruct a 26 degrees of freedom pose of the person's hands and fingers. The result is a 3D model that includes the configuration and surface geometry of the hand. Now let's proceed to the next part of our presentation, the review of classic computer vision algorithms, which are widely used in extended reality. I will provide a general review of some of the popular algorithms such as optical flow, Kalman filters, and SLAM. So let's start. The first algorithm is optical flow. Nowadays, it is mainly used for motion estimation, but we can rewrite this problem a little bit and try to use this motion in order to solve the problem of point tracking in augmented or mixed reality. Let us begin with a high-level understanding of optical flow. Optical flow is the motion of objects between consecutive frames of sequence caused by the relative movement between the object and the camera. The problem of optical flow may be expressed as in this image, where between consecutive frames, we can express the image intensity, I, as a function of space, x, y, and t. In other words, if we take the first image, this frame on the left side of the presentation, and move its pixels by delta x and delta y in this direction over time t, we obtain a new image I, where our x will be equal to x plus delta x, y plus delta y, and t plus delta t. So first we need to assume that pixel intensities of an object are constant between consecutive frames. So our actual pixel intensity on this position and on this position before movement should be the same. Second, we need to take the Taylor series approximation of the right-hand side of our equation and remove common terms in order to simplify this to this condition. And third step is we divide by time derivative to get the optical flow equation, where U is actually equal to derivative of x over derivative of time, and V is equal as derivative of y over derivative of time. And those three derivatives are the image gradients along the horizontal axis and the vertical axis, and also the time. Hence, we conclude with the problem of optical flow, that is solving the U and V to determine movement over time. Most attentive of you may notice that we cannot directly solve the optical flow equation for U and V, since there is only one equation for two unknown variables. And it is simply impossible to solve this equation here. So now I will show LUCAS-KANADE method, which is able to solve this problem. Lucas and Kanade proposed an effective technique to estimate the motion of interesting features by comparing two consecutive frames. This LK method works under the following assumptions. The first assumption is that two consecutive frames are separated by a small time increment, such that objects are not displaced significantly. In other words, the method works best with slow-moving objects. And the second assumption is that a frame portrays a natural scene with textured objects exhibiting shades of gray that change smoothly. So first, under these assumptions, we can take a small 3x3 window around the points which we want to track and assume that all 9 points have the same motion. This may be represented as on the image here, where Q1, Q2, Qn, and so on denote the pixels inside the window, which is in our situation n equals to 9 because we have a 3x3 window. And intensity over x, intensity over y, and over t denote the partial derivatives of image with respect to position x, y, and also time t for pixel qi at the current time. So here, this is just the optical flow equation that we described earlier for each of the n pixels which we have in our window. The set of equations may be represented in the following matrix form, where A multiplied by B is actually equals to our B vector. And please note that previously we faced the issue of having to solve for 2 unknown variables with 1 equation. And now we face a problem to solve for 2 unknowns with 9 equations, which is overdetermined. Second, to address the overdetermined issue, we apply least squares fitting to obtain the following 2 equation to unknown problem. Actually, from here, where Vx is equal to u, the moment of x over time, which is the moment of x over time, and v of y denotes the moment of y over time. And solving for those 2 variables completes the optical flow problem. And this is how it is done. Let's move next. The next is Kalman filters. And Kalman filters are very popular for tracking obstacles and predicting current and future positions. They are used very often in augmented reality and mixed reality, as they are able to provide stable object tracking even with some occlusions. Let's take as an example bounding box tracking using Kalman filter. The work of algorithm starts after a box was detected, and when the association is made, predict and update functions are called. These are actually the only functions which Kalman filter has. They implement the math of Kalman filters composed of formulas for determining state or mean and covariance. Mean and covariance are what we want to estimate here. Mean is the coordinates of the bounding box, and covariance is our uncertainty of this box having these coordinates. So here, mean, which is an x, is a state vector. It is composed by coordinates of the center of the bounding box, size of the box, and the change of each of these parameters, velocities. When we initialize this parameter, we set velocities to 0. They will then be estimated by the Kalman filter. The next is the covariance, which is a P matrix here, and it is our uncertainty matrix in the estimation. We will set it to an arbitrary number and tweak it to see results. A large number means a larger uncertainty in the situation. And so this is actually all we need to estimate, a state and an uncertainty. There is 2 steps for a Kalman filter to work, the prediction one and update. Prediction will predict future positions, update will correct them and enhance the way we predict by changing uncertainty. With time, a Kalman filter gets better and better to converge. Now at time t equals 0, we have a detection of bounding box. For this bounding box, we need to initialize our Kalman matrices with coordinates of the bounding box. And next, at time t equals 1, we have new bounding box of the same object. We predict the actual bounding box at time t from the bounding box at time t minus 1, and then update our prediction with measurement at time t. Prediction phase is matrix multiplication that will tell us the position of our bounding box at time t based on its position at time t minus 1. So imagine we have a function called predict in our class of Kalman filter that implements this math. All we need to do is to have correct matrices f, q, and u, And we will not use the U vector as it is used to estimate external forces, which we can't really do easily here. And now we have a question, how to set up the matrices correctly. And the first matrix is the state transition, which is the F matrix. F is the core implementation of what we will define. What we put here is important because when we will multiply X by F matrix, we will change our X and have a new X called X prime. As you can see, F is an 8 by 8 matrix, contains a time value delta t, and this delta t is the difference between current frame and former frame timestamp. We will end up having Cx prime equals to Cx plus delta t multiplied by Vx, like here this Cx multiplied by delta t and Vx, just simple matrix multiplication, and so on for all our next steps. In this case, it means that we consider the velocity to be constant. We therefore set up F matrix to implement the constant velocity model. There are a lot of models we can use depending on the problem we want to solve. The next matrix is the covariant matrix, which is Q. Here it is on this slide. And this Q matrix is actually our noise matrix. It is how much confidence we give in the system. Its definition is very important and can change a lot of things. Q will be added to our covariance matrix and will then define our global uncertainty. It depends on different situations, but for example, here we can put very small values for our covariance matrix, like 0.01, and change it with time. The next step is an update step. An update phase is a correction step. It includes the new measurement set and helps to improve our filter. The process of update is to start by measuring an error between measurement Z and predicted mean. The second step is to calculate a Kalman gain, which is K in this example. And the Kalman gain is used to estimate the importance of our error. We use it as a multiplication factor in the final formula to estimate Ux, which is our predicted position. And again, we have the same question, how to set up the matrices correctly. The first matrix is Z matrix, and it is the measurement at the time t. We don't input velocities here as it is not measured. We simply put the measured values. The next matrix is a measurement matrix. It is H in our example, and it is a 4 by 8 measurement matrix. It simply makes the math work between all of different matrices. We put the ones according to how we define our state, and its dimension highly depends on how we define our state. The next matrix is the measurement noise. And this R matrix is our measurement noise, and it's the noise from our sensors. So here we need to define a noise for our prediction algorithm in terms of pixels. It will be arbitrary. We can say that the noise in terms of the center is about 1 or 2 pixels, while the noise in the width and height can be bigger, for example, 10 pixels. And so actually this is all for the Kalman filters and how they work. And the next algorithm which I want to shortly talk to you about is the SLAM. And for augmented reality, the device has to know its 3D position in the world and the object position which surround it. The device calculates this through the special relationship between itself and multiple key points in 3D space. And this process is called simultaneous localization and mapping, or SLAM for short. When you first start an augmented reality application using, for example, Google AR Core or Apple AR Kit or Microsoft Mixed Reality, the system doesn't know much about the environment. It starts processing data from various sources, mostly from the camera. And to improve accuracy, the device combines data from other useful sensors like the accelerometer and the gyroscope. And based on this data, the algorithm has two aims. The first one is to build a map of the environment, and the second one is to locate the device within that environment. SLAM algorithm works by updating a probability distribution of where every position of key points could be each frame. For some points, you might have a higher precision. For others, the uncertainty may be large. So to solve this problem, there are several frequently used algorithms to calculate the positions based on uncertainties. Those are the extended Kalman filter, which we discussed previously, but in this case, it is a little bit different because it used to approximate nonlinear system. It also can be a maximum a posterior estimation or a bundle adjustment. To make augmented reality work, the SLAM algorithm has to solve the following challenges. The first one is the unknown space, because our device actually doesn't know the environment in which it starts working. The second is uncontrolled camera. For current mobile phone-based augmented reality, this is usually only a monocular RGB camera. It should work in real time, and also it should be drift-free. The image on the right is from the mono-SLAM algorithm showcases what you want to achieve by using SLAM. You want to find the tracked feature points, the relation in space, as well as the inferred camera position. Now let's talk a little bit the SLAM architecture. The system is actually made up of 4 parts. The first one is sensor data. On mobile devices, this usually includes the camera, accelerometer, and gyroscope. It might be augmented also by other sensors like GPS, light sensor, depth sensors, and whatever else. The next step is the front-end part. It is the first step of this part is a feature extraction. These features need to be associated with landmarks, key points with a 3D position, also called map points. In addition, map points need to be tracked in a video stream. Long-term association reduces drift by recognizing places that have been encountered before. It is also called loop closure. The next step is the backend of SLAM, and it takes care of establishing the relationship between different frames, localizing the camera with pose model, as well as handling the overall geometrical reconstruction. Some algorithms create a sparse reconstruction based on the key points. Others try to capture a dense 3D point cloud of the environment. SLAM estimate is the final step of this architecture, and it is the result containing the tracked features, their locations and relations, as well as the camera position within the whole world. And now let's take a closer look at a concrete SLAM implementation, which is called ORB SLAM. A very well-working and recent algorithm is ORB SLAM, which works with monocular RGB camera. Also, it has a successor, which is ORB SLAM 2, which adds support for stereo or depth cameras, in addition to a monocular RGB camera. ORB SLAM is a visual algorithm, so doesn't use any odometry by accelerometers and gyroscopes. It only uses a raw camera data. And considering that, the algorithm still works great and the results are really impressive. Many algorithms have the mission to find key points and to generate descriptors. The traditional SIFT and SURF algorithms are always used as reference, but are generally too slow for real-time use. As the name implies, the ORB SLAM algorithm relies on the ORB feature tracking algorithm instead, and ORB is based on the same underlying method for finding key points and generating descriptors as the BRISC algorithm. In general, ORB SLAM analyzes each frame for key points. These are then stored in a map together with references to keyframes where these key points have been detected. This association is important. It's used to match future frames and to refine the previously stored data which we had. One of the most interesting parts of SLAM is how key points found in 2D camera frames actually get 3D coordinates, then which we call them like map points or landmarks. Whenever the algorithm gets a new frame from the camera, it first performs a key point detection. These key points are then matched to the previous camera frame, and the camera frame motion so far provides a good idea on where to find the same key points again in the new frame. This helps with the real-time requirement. The matching results in an initial camera pose estimation. Next, ORB-SLAM tries to improve the estimated camera pose, and the algorithm projects its map into the new camera frame to search for more key point correspondences. If it's certain enough that the key points match, it uses the additional data to refine the camera pose. New map points are created by triangulating matching key points from connected frames. And the triangulation is based on the 2D position of the key point in the frames, as well as the translation and rotation between the frames as a whole. Initially, the match is calculated between two frames, but it can later be extended to additional frames. The next step is a loop detection. And it is another key step in a SLAM algorithm, and also from loop detection, it is loop closing, which we will talk on the next step. ORB-SLAM checks if key points in a frame match with previously detected key points from a different location. If the similarity exceeds a threshold, the algorithm knows that the user returned to a known place, but inaccuracies on the way might have introduced an offset. And by propagating the coordinate correction across the whole graph from the current location to the previous place, the map is updated with the new knowledge. And it is actually how the last step of the SLAM works, which is loop closing. And so, yeah, that's all for the SLAM algorithm. And now let's move to the final part of our presentation. And this part, you can actually try the augmented reality by yourself. So here you can see a QR code on the right side of the presentation. You can scan it and will be redirected to our corporate website, where you can download our internal application, which is named SoftServe IR Business Card. And there are two possibilities to download it from Play Market for Android devices or App Store for iPhones. And then you can try to use this application on the business card, which is on the left side of the presentation, and try to get some immersive augmented reality experience about our company. So that's all for my presentation today. Thank you for your attention. And now I think we will have some Q&A session. Also, I will leave this slide for several moments on the screen in order for you to download the application and try it by yourself. Thank you.